Okay, so the last speaker for the day is Kashyap Rajeevsarathy, who will talk about estimating the distances between hyperbolic structures in the moduli space.
Thank you, Sabya. And I'll thank the organizers for, giving me this opportunity to be a part of this conference. And so far, all the talks I've heard have been very illuminating, and I've had an amazing experience here. And so to get to the topic that I'm about to speak about, I will require a basic background in mapping class groups and Teichmüller theory. And thanks to Professor Yamada, Professor Parker, and other people who have spoken in the morning sessions, I don't have to cover the material very deeply. So I'm just going to review most of the things that have already been discussed in this conference a little bit, just for completion. And I'll go ahead with what I'm about to talk about. Okay, so this is the overview of the talk, and we'll review some mapping class groups and Teichmüller theory basics, and then I'll talk about the Pans graph and the Brock quasi-isometry, then a specific class of irreducible actions, cyclic actions on surfaces called type 1 irreducible actions, and how do you estimate structures, hyperbolic structures that realize these actions as isometries. Okay, so most of you are familiar with this. Here the setting is finite type surfaces, okay? So we are talking about closed, connected and oriented surface. Initially, I'm defining mapping class group in generality. We are looking at homeomorphisms that restrict identity on the boundary and preserve the set of punctures. And then you take the path component of that, you give that the compact open topology and take the path components of that, and path component of the identity, and that's a normal subgroup, and you quotient this homeomorphism group by that normal subgroup, you get the mapping class group. Okay, and you can also think of that as the path components, space of path components of homeomorphism group. And the elements of the mapping class group are called mapping classes. And for now, for this talk, I'll be focusing on the closed orientable surface or oriented surface of genus G. Okay, which I'll denote by SG. And it's known that for the sphere it is trivial, the mapping class group is trivial, and the torus it is SL2Z, and so on. And in general, the mapping class group is finitely generated and presented. So if you have any questions, people who are not probably familiar with mapping class groups, I'll be happy to review any of these things or recall any of these things. And say a little bit about the Nielsen-Thurston classification, about what are the kinds of mapping classes that we have. So we call a collection of pairwise disjoint non-isotopic essential simple closed curves on the surface as a multicurve. And a mapping class is periodic if it has finite order. It's reducible if it preserves a multicurve. And it's pseudo-Anosov if it preserves a pair of transverse measured singular foliations on the surface. And the Nielsen-Thurston classification, it asserts that for each mapping class, at least one of the following holds. So it's not like mutually exclusive. There are intersections between the classes of periodics and reducibles. But the pseudo-Anosov class is sort of exclusive. If something is pseudo-Anosov, it cannot be one of the other two. Okay? So that's basically like, of course, we won't be, talking a lot about reducibles and pseudo-Anosovs. We'll be, in this particular talk, we'll be focusing on periodics. Okay? All right. So just a quick review of Teichmüller space. A lot has been spoken about it already in this conference. I don't have to. So you have this. So you have an hyperbolic structure on the surface, and here I'm taking the closed orientable genus G surface, right? And a hyperbolic structure or marking, I'm taking it as a diffeomorphism from phi from SG to X, where X is a complete hyperbolic metric of finite area. Okay? And two such markings are equivalent if there is an isometry between X1 and X2, such that this diagram commutes. That is, F composed with phi1 is homotopic. It commutes up to homotopy or isotopy. So that is what F composed with phi1 is homotopic to phi2. And the Teichmüller space is the space of all equivalent markings. And We have already discussed Fenchel-Nielsen coordinates on the Teichmüller space, but I'll do a quick recap of that. You consider a Pans decomposition. It's a collection of 3G minus 3 curves on your surface. This is the genus G surface. So a Pans decomposition will have 3G minus 3 curves, and that will break the surface or decompose the surface into pairs of Pans. And also you need to select a seams multicurve, a collection of curves whose intersection with each pairs of Pans on the surface is the union of 3 disjoint arcs. So let me explain that. So for example, if you take genus 2, this is a Pans decomposition. 3G minus 3. The seams curve for this would be something like this, and this curve. Okay? So if you break that curve, and you see it in each Pans decomposition, it will be a union of 3 disjoint arcs. And so you choose such a collection. That such a collection is not difficult to choose. There are other ways of choosing it, but I'm just saying it. Then the I twist parameter is defined by, theta I is 2 pi times the twist. So for each curve, there will be an arc that comes from the left and comes from the right and hits it. And so you twist it with respect to this arc and that arc, and you take the difference and divide it by the length of gamma I, and that will give you this is the formal way of defining the twist parameter. And of course, there's another way, like when you bring the Pans decomposition together and you join them, you ensure that the lengths of the curves that you are joining are equal. And when you join them, you give a twist on one side. That's another way of looking at it. So that is that twist parameter. You can see it any which way you want, but it's essentially the same idea. So yeah, the Fenchel-Nielsen coordinates are by you take the Pans decomposition and you take the lengths of all this. That's a typo here. It's alpha 3G minus 3. Sorry about that. And so you have the lengths of the curves under that. You take a structure in the Teichmüller space, right? And you take the lengths of the unique geodesic representative of the pre-homotopy class of the curves in the Pans decomposition, and the twist parameters associated with those curves. And then you map and you get a 6G minus 6 coordinates for each structure in Teichmüller space, right? And then from that, we can show that the Teichmüller space is homeomorphic to R6G minus 6. Okay, any questions on this? Should I move ahead? All right, yeah. Right. Yeah, you push it to the hyperbolic surface and see that. Right. Right. So I already, yeah. Now let's talk a little bit about the Weil-Petersen metric. So again, this has been discussed in this conference already. And so I'll just do a quick review of what has been said. So how does this metric come about? So basically you take any structure or any class in Teichmüller space, it's represented by a Riemann surface, and its cotangent bundle can be identified with the space of holomorphic quadratic differentials. And this comes equipped with the inner product, right? An L2 inner product, Hermitian inner product. And that is given by this. And here you can see that this is integrating over this Riemann surface of Q1, Q2 bar divided by rho of x squared, where rho of x is the hyperbolic metric, right? And you take the square of the hyperbolic metric. And this introduces an inner product. This inner product at the level of cotangent bundle introduces an inner product at each point in the tangent space of the Teichmüller space, and which in turn induces a Riemann metric on the Teichmüller space called the Weil-Petersen metric. Okay? And this I'm going to denote by mu of WP. That's my notation, probably not the best of notations, but that's the notation I'm going to use to denote the Weil-Petersen metric. And the Teichmüller space with respect to the Weil-Petersen metric, it has already been said that it's a Kähler manifold. And because what is a Kähler manifold, if you don't understand this technical definition, it's sort of like a Kähler manifold is a marriage of sort of a complex manifold, a Riemannian manifold, and a symplectic manifold. So, and where the structures are sort of consistent. All three structures are consistent. You can think of it like that. So, but the technical definition is what I have here. If you take the exterior derivative, d of the exterior derivative of the imaginary part of the Hermitian metric on the Teichmüller space vanishes. Okay? So, and what do we know about this Weil-Petersen metric? We know that the thing that will be very relevant to me, at least, there are several properties. Professor Yamada said that it's not complete. We know that it's not complete. And but the property that I'm interested in is particularly if you take isometries of the Teichmüller space with respect to the Weil-Petersen metric, it is the extended mapping class group. I'm not defined what the extended mapping class group is. The extended mapping class group also includes mapping classes that are represented by orientation reversing homeomorphisms on the surface. So whatever we define the mapping class group is generally for orientation preserving mapping classes. This also includes orientation reversing mapping classes. And because of that, it acts by mapping class group acts by isometries. And the important thing, this metric that is there on the Teichmüller space will descend down to the quotient under that action as a metric on the quotient. And that quotient is the Moduli space. Okay. So you have this action by isometries, by mapping class group on the Teichmüller space with respect to the Weil-Petersen metric, and that descends down to a metric via this action to the Moduli space. And that's a space we'll be concerned with. So when we're talking about estimating distances here, I'm talking about the Weil-Petersen distance that I'm trying to estimate in this talk, right? Okay, let me talk a little bit about the Nielsen realization theorem. I mean, it goes a little bit, I mean, it's got a very interesting history, but I don't have time to cover all of that, but it goes way back to the times of Nielsen. And it basically says that if you take a finite subgroup of the mapping class group, does it act on the surface? So essentially, that's what the theorem says. And yes, I think Nielsen and Fenchel proved it for the cyclic case. Yes, it's true. And then there was a bunch of people over the next few decades who proved it for various kinds of subgroups of the finite subgroups of the mapping class group, until it was completely settled by Stephen Kirchhoff in 1983, where he said that if you take any finite subgroup of the mapping class group, it acts on the surface. It not only acts, it acts by isometries. In other words, there is a hyperbolic metric on this surface under which this mapping class group, or this a subgroup of the mapping class group, are realized as an isometric group of that hyperbolic surface. Okay? So the important thing about, just like we saw in what we saw in the Teichmüller space, we had a action by isometries and descended down to an action to a metric on the quotient. The similar thing happens here too. So you can basically associate when you have a finite subgroup that acts by isometries on the surface, it descends down to a structure on the quotient orbifold, and the quotient orbifold is well defined, and it's a hyperbolic orbifold, and you can associate to each subgroup of the mapping class group a corresponding or a quotient orbifold, right? And the Nielsen realization theorem, so another way of seeing the Nielsen realization from the Teichmüller theory perspective, it says that if you take a finite subgroup of the mapping class group and you take the restricted action, the action of the mapping class group, and you restrict it to that finite subgroup on the Teichmüller space, that has a fixed point. Okay? And that is how I think Kirchhoff proved it. I think the proof of Kirchhoff proved that if you take a finite subgroup and you act it on the Teichmüller space, it has a fixed point, and he used earthquake flows and on the Teichmüller space to prove that. And in general, it will not be just a fixed point. If you take any finite subgroup of the mapping class group, this is going to be an even dimensional submanifold of the Teichmüller space, right? And that is because it is this Teichmüller space, this submanifold, which is a fixed point set of this finite group action, can be identified with the Teichmüller space of the orbifold. That's equivalent to saying that the structures that realize it as isometries are essentially the structures that you can put on the quotient orbifold and pull back under the properly discontinuous, the branch cover induced by the action. Is that okay? Any questions so far? Yeah, yeah. Like this. So, but it's in general, it's difficult. You can say it will be some R2K, or it is homeomorphic to some R2K, but it's the difficult question is how it is embedded. Exactly to tell you that embedding is little difficult to predict normally because it can be crazy. Okay? Yeah. So let me talk a little bit about, I said the mapping class that I'll be concerned with is periodic mapping class, but I'll talk about a specific class of periodic mapping classes called irreducible periodics. So, first of all, let me talk about what does irreducibility mean in the mapping class group. So we already know that something is reducible if it preserves a multicurve, right? So a non-reducible mapping class is called irreducible, is called a irreducible mapping class, basically. Something that's not irreducible, not reducible is called irreducible. And in mapping class group, an irreducible mapping class, in mod SG particularly, it is either periodic or pseudo-Anosov. Okay? So our case, we are only concerned with periodics and the fact that what if it's periodic and irreducible, right? So it's a result of Jane-Gilman that says that a mapping class group, a cyclic subgroup is irreducible if and only if the corresponding orbifold is a sphere with 3 cone points. Okay, that is the orbifold associated with it, with that action, cyclic action, is a sphere with 3 cone points, right? And essentially, if you have a sphere with 3 cone points, what you can do is, and the cone points are going to be ordered. So we are looking at basically an object like this, not. So yeah.
Your original surface is compact?
Yeah, it's compact. Yeah, close to orientable surface.
No cast.
Yeah, no cast, no nothing. Right, so that is the sort of orbifolds that you're going to get for these kind of actions. The surface will quotient down into something like this. And the interesting thing is, what will happen is, so already you can associate to each irreducible action these cone points, the orbifolds. This is called the orbifold signature. This orbifold will have signature N1, N2, N3, and genus 0. Then you can pull back these points, these cone points under the branch covering, and you can study the rotation angles around the corresponding orbits that were mapped down to these cone points. That is some geometric information that you can associate to this action also. And this orbifold signature information, together with that geometric information, captures that action up to conjugacy. This is a result of Nielsen. So basically, you can see here this simple data that I have associated to this action. N1, N2, N3 are the orders of the cone points, and the CI, C1, C2, C3 are basically the geometric information concerning the rotations around the orbits when you lift the cone points under the branch cover. Okay? So the important thing to note, since it's an irreducible action, the H action of such actions on Teichmüller space is a unique fixed point. Is a unique fixed point. As you can see, if the quotient is going to be something like this, there's only one structure you can put on this to lift up. So that's a unique structure that will realize these actions as isometries. That fixed point is represented by an hyperbolic structure, and that is a unique structure that's going to realize such actions as isometries. Any questions? All right. Yeah. We are getting that. We're just about it. Yeah, definitely. We'll give you many examples of it, right? Okay, let me talk about, yeah.
Is the fixed point of this H,
Right, on the Teichmüller space.
but is it necessarily isolated in the Teichmüller space? In other words, in terms of the
Right. So,
sets of other elements.
No, that might not be the case. That might not be. Yeah. There might be other. Right. For example, if you take, for example, a power of this action, a power of F, that will also be sometimes a cyclic group. That will include this fixed point. The fixed point. I wouldn't believe so. I wouldn't believe so. It's not like it will touch some other submanifold of some other subgroup. I would believe that always. Right. Okay. So let me talk a little bit. We talked about the Weil-Petersen metric on the Teichmüller space, and this I will talk about the Pans graph and the Brock quasi-isometry. Okay. So the Pans graph. How do you define the Pans graph? So you take two Pans decompositions, P1 and P2, of the surface. In this, again, we are talking about the closed-oriented surface of genus G in this case. They are said to differ by an elementary move. If P2, the Pan number 2 is obtained from Pan number 1, right, by replacing a curve with another that intersects it minimally. So for example, let me draw it here. This is a Pans decomposition. Let me call this P1, right? And I give you another Pans decomposition here. So maybe I'll do it slightly differently. So I'll take this one. Okay. This makes it a little bit easier. So what I just did here, that this will also be a Pans decomposition. This will also be a Pans decomposition. What I've done here is that this is so I replaced this Pan by another Pan, in which this curve has been replaced by this curve that intersects it minimally in the surface. Essentially, both are Pans decompositions. And that is basically the philosophy behind the Pans graph. It's as simple as that. So the vertices are all possible Pans decompositions. Okay? And two vertices are joined by an edge where the vertices represent pairs of Pans if they differ by an elementary move, a single elementary move. So for example, if you take these two things, they will be vertices in the Pans graph and they will be distance 1. That means in the Pans graph, these two vertices will be joined by a single edge. Okay? And you can make this even better, like you can find, so that is the Pans graph. It's very simple to define, easy to understand. You can draw it out yourself and try to figure out like distance 2 stuff, distance 3 stuff, and all that. Okay? So the important thing to note is that why is this of any significance? First of all, it's a result of Dan Margalit, right? Which showed that if you take the automorphism group of the Pans graph here, it's actually, the Pans graph can be extended to a complex, but I'm only taking the one skeleton of it, the Pans graph. So the Pans graph is equal to the extended mapping class group. So you take all automorphisms of the Pans graph, it's actually the extended mapping class group. And further, it was shown by Brock. This is the part that we will be interested in, that the Pans graph with the natural path metric, like it's a graph, right? You have a path metric on the graph. That models the Teichmüller space with the Weil-Petersen metric. Or is it quasi-isometric to the Teichmüller space with the Weil-Petersen metric? Okay? So that's the reason. So you see the parallel, right? What is happening in the Pans graph world and what's happening in the Teichmüller world. So that's why we. Any questions on this? Yeah. No, it's a graph automorphisms. Automorphisms as graphs. It's a graph, right? Yeah. Huh? You were saying something? Yeah. Okay.
It's not a proper graph. It doesn't have bounded values. Points have infinite degree in the Pans graph.
Right. I would, yeah, I would imagine so. Yeah. So, right. So bursts. So let me say a little bit about this quasi-isometry. How does this work? Okay. So bursts show that there is an universal constant called the burst constant, such that if you take any structure in Teichmüller space, then you can always find a Pan's decomposition, the length of whose curves are bounded above by this constant. And this constant is a universal constant because it depends only on the genus, right? So you can always, so for any structure in the Teichmüller space, you can find a Pan's decomposition, Px, the length of whose curves are bounded above by this constant. Okay? And Buser, I think this is the reference I could find for it, but I'm sure there was a paper where he proved this. I don't know that paper, but this is a book that it's not true, right? Oh, really? Because I couldn't find anything better than this. Like I said, this is the one I could find. This is definitely there in this book, but so Buser derived a lot of bounds for this burst constant, and the most prominent are these lower and upper bounds, which is root of 6g minus 2 is a lower bound, and so here is a mistake. So there's a typo here. This is less than equal to bg less than equal to 26 times d minus 1. I'm sorry. Yeah. Sorry about that. That's hilarious. Okay. Right. Yeah. So this says that you shouldn't work on your presentation at nights when you're sleepy here. Right. Anyway, so this lower bound for the burst constant is this, and upper bound is that. Okay. So that is the thing that you need to think. And so the important thing is, using this burst constant, you can define a sub-level set in the Teichmüller space. Right? So this also comes from Burst's work. I don't think this is credited to Brock. But what you can do is, for V of P, for any Pan's decomposition P, consider the sublevel space V of P is all structures in Teichmüller space such that if you take the maximum of the lengths under the structure of any alpha, where alpha belongs to this P, it is less bounded above by the burst constant. Okay, and you can show using the work of Burst that this B of P indeed cover Teichmüller space. These sublevel sets cover the Teichmüller space. They are convex, right? And the diameters are bounded above by another universal constant. Okay, dg. That depends only on the genus. So how do you define the quasi-isometry? It's pretty simple. Like you take defined by a map Q from the vertex set of the Pan's complex, that is the zero skeleton of the Pan's complex, to the Teichmüller SG. So such that what you take, if you take Q of any P, you ensure that it goes into V of P. Right? That is essentially captures the quasi-isometry. Right? And under this quasi-isometry, what is the comparison? How do these two metrics compare? If you see this, if Px and Py are Pan's decompositions such that X is in Vpx and Y, Px is this Px that I have on the top here. That is this P. So if you take X in Vpx and Y in Vpy, then the distance in the Pan's graph between Px and Py is comparable to the distance between the Weil-Petersen metric between X and Y. Is that making sense? Everybody? Yeah.
The VP is also bounded independent.
I'm not sure about that. At least I don't know. I'm not sure about that. I don't want to give an answer that I'm not sure about. Maybe we can talk about that. Right. 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 Sure. Yeah. it will be. It will be non-empty. Yeah, that's correct. Right, so we talked about irreducible actions, cyclic actions, which are actions whose corresponding orbifolds are like this, a sphere with 3 cone points. But within this class of actions, we are going to focus on a particular subclass of actions, okay? And so these are called type 1 irreducibles. At least this is the name I have given, but I'm sure there's a better name for it. So the irreducible type 1 cyclic action is of type 1 if the isometry representing F. So we know that it acts by isometry because, so the mapping class is represented by an isometry. It has a fixed point on the surface. Okay? Equivalently, how can you say that? You can say that if you take the conjugacy class that I talked about, which comes from the Nielsen data, that will have an N here, definitely. Because normally it was C1, N1, C2, N2, C3, N3. The N3 you can replace by an N. N is the order of the, sorry, this N is the order of H. So let me also make a mark of that. I didn't mention that. Order of H equals N. That's what I meant to say. That N is order of H, order of this cyclic action. Okay? Okay? So, what we did some years back, what we showed is that these actions are very special. So these actions can be realized. So we know all these actions have a unique hyperbolic structure, realizing them as isometry. So these actions are realized by a very particular hyperbolic structure, which is given by a hyperbolic polygon, a regular hyperbolic polygon, and you rotate that polygon in a certain way, and that realizes these actions, all these actions, these type 1 actions. Okay? And not only that, we went on to say that these actions, these structures that realize these actions are sort of like the building blocks, right? If you want to realize a structure realizing an arbitrary cyclic action, you can take these canonical structures that we described and put them together in a certain way, like through certain compatibilities, and construct arbitrary cyclic actions. Now here, what I'm concluding is a little bit more than that. I'm also saying arbitrary subgroups. The reason for that is that if you take an arbitrary finite subgroup of the mapping class group, it will be finitely generated, F1 to Fn, let's say. And each is a cyclic action. So the fixed point set of that subgroup will be the intersection of the fixed point sets of the individual cyclic generators. Right? The fixed point set of the subgroup will be the intersection of the fixed point sets of the individual cyclic generators. So these are essentially the building blocks of the actions that realize arbitrary subgroups as isometries for any arbitrary finite group action on a surface. Okay? So this was the theorem that we proved, and it was Shiv Prasad, me, myself, and Vidyut Sankhi who's sitting here. And we showed that these hyperbolic polygons, we can actually describe them. They are 2n gons. We gave an explicit description of the side pairing and what is the rotation that you need. Okay? So it's very technical, but we gave a complete description of this polygon. So this essentially is the representative of the unique fixed point in the Teichmüller space that these actions fix, right? These polygons represent that unique fixed point in Teichmüller space. They are the hyperbolic structure that fixes it. They give the hyperbolic structure. So let me give you 2 basic examples of these polygons. These are the very standard examples. I've taken these examples. Generally, these polygons are complicated. The side pairing is complicated. I don't want to deal with that in this talk. So I took the standard examples of these polygons. So for example, genus 2, you can take these 2 polygons, right? On genus 2, you can take, this is an octagon, this is a decagon, right? In both polygons, there's a very simple pairing. You are pairing opposite sides. Okay, normally when the ones that we learn in a basic course in algebraic topology, where we derive the presentation of the fundamental group of genus 2, here this polygon would have the product of 2 commutators in its boundary. But that's not the pairing we are taking here, because that pairing doesn't realize the action that I'm talking about here. Okay, this action I'm talking about is realized by this particular pairing. And this is a rotation by 2 pi by 8, and this is a rotation by 2 pi by 10. And both these, so these are hyperbolic structures on genus 2. This realizes a Z8 action, and this realizes a Z10 action. And interestingly, it is known that these two are two of the largest order actions on genus 2 surface. The largest order action on any genus G surface is cyclic action is 4G plus 2. So this same two polygons will realize the largest two order cyclic actions on any genus G surface. In general, this will be a 4G gone, that will be a 4G plus 2 gone. That's the only difference. The pairing is exactly the same. In one polygon, the rotation will be 2 pi by 4G. The other polygon, the rotation will be 2 pi by 4G plus 2. That's it. That's a generalization of these polygons. So there's a big family of polygons that comes from. Okay? These things? Yeah, this is the order. This is the genus of the quotient orbifold, which in this case is 0, because all these actions correspond to orbifolds that look like this. And 2, 8, and 8 are the orders of the cone points. And 1, 1, and 3 are the data of the, when you lift those cone points across the cover, the branch cover, to the surface, the rotation angle in the tangent space induced around the orbit points. So it's all technical, I'm not getting you. So pretty much all this information is there, hidden in this polygon. You can recover this completely in this polygon. Okay? So let me go over some recent work that, we just submitted, we just got done. So that I think I covered the background for this work. And this joint work with Athanase Bhattacharya and Suman Paul. So using this idea, this particular, the realization, how can we estimate? So my focus is to take two such structures, like that these special polygons that realize these irreducible type 1 actions, and estimate the distance between them. There are specific points that I'm picking in Teichmüller space, and I'm trying to estimate the distance between them. But there is a catch. The way we have written this particular theorem, we are associating this structure that we are giving to a conjugacy class, because this data represents an entire conjugacy class. So it's not going to be one single structure. It's going to be an orbit of structures in the Teichmüller space. So it will be this structure that, for example, let me go here. For example, if you take this structure, if you're looking at this conjugacy class, it will be this structure and the pullback of this structure in Teichmüller space with respect to all mapping classes. That is the set. So the estimate, essentially we are trying to estimate the distance between this orbit and that orbit in the Teichmüller space. That's why we descend down to the Moduli space, where it will be a single point. You're essentially estimating the distance between these structures in the Moduli space. In the Teichmüller space, it will be a distance between two orbit sets. Okay? Okay, so the question is, can one provide, preferably, that's why I've written in brackets, a combinatorial method for estimating the Weil-Petersen distance in the Moduli space between structures realizing type 1 actions. So the reason why I'm focusing on type 1 actions, as I told you, they are the building blocks. I believe at least that if I can estimate the distance here, I can find a way of estimating the distances between arbitrary structures, using this idea that, arbitrary structures are put together using these structures, right? So given two canonical polygons, we address this question with the following simple algorithm. The algorithm is very simple. Determine a Pan's decomposition. The first catch is, the Burst result asserts that if you take any structure in the Teichmüller space, you can find a Pan's decomposition, the length of whose curves are bounded above by the Burst constant. So that's sort of existential. So can you actually determine such a decomposition? That's the first step. That's the first hurdle. So the first hurdle is, determine a Pan's decomposition in which the length of all curves are bounded above by the Burst constant. And this Pan's decomposition, we are going to call it a admissible Pan's decomposition. Okay? And then you estimate the distance between these two Pan's decompositions in the Pan's graph first. Keep that aside. That's not very difficult. I'll tell you how to do that. And then using this distance, you get an estimate for the distance between the orbits that I spoke about, the pullbacks of these structures in the Teichmüller space. And that in turn gives you an estimate for the structures between the corresponding hyperbolic structures in modular space. It's as simple as that. Any questions? I'll use the quasi-isometry to get the bound. Yeah, I think they are known. Like I don't know them, exactly what they are, but I think he gives an idea of what they are, how he gets them, and it's all there. What is that?
Don't the quasi-isometry
Yeah. So this bound will involve the constants. Yeah, that's absolutely correct. Yeah. So if you know the constants, you can get this estimate, and that's kind of things are known about it. I think at least we can kind of nail it down. In the paper, he talks about how he gets those constants and all that. But I'm not getting into those details, but for me, it's just that I can estimate it. If I know the quasi-isometry and the constants, I can estimate it. Okay, so when we looked at these structures, and we want to say, okay, let me try to get a Pan's decomposition whose lengths are bounded about by the burst constant. We had no idea where to start. So the easiest thing to imagine when you got a polygon is slice it in the most obvious way, right? So what we tried was that, you take these geodesics, okay? At least for these polygons, these are the geodesics. You take the geodesics, like you see that, right? You can cut it. So you take these geodesics and cut the polygon across, or decompose it into pieces using these geodesics. And similarly for the other polygon. And then we thought, okay, what does this give? That is a problem. There's a problem with this thing. It's that it's good, but each piece will not automatically become a Pan's decomposition or a pant. It might be something like an X piece, like some structures will give you some sort of an X piece, or some might be an annulus, something like that. I mean, it might not be, you might not immediately get a Pan's decomposition. But what we wanted to show, if you see here, this gamma I are these lines in these polygons. And I also describe another geodesic, which are not relevant to these particular polygons, but they will be helpful for more arbitrary polygons. We will need those geodesics joining the midpoints of certain sites also. So we broke the polygon this way, okay? And as you can see, if you break it apart, these are the kind of pieces that you will get, right? You can easily see it, like if you break these polygons, these are the kind of pieces you will normally get, right? And then what you want to do is, once you break them apart, you want to put them back together in a certain way. It's simple topology, like you want to put them back together, keeping track of the Euler characteristic and stuff like that, and in which order you put them back together, okay? It's as simple as that. And so what we saw is that if you see, these are if you take BI to be the initial point of AI, W to be the terminal point, these are the possibilities that you will get when you break them apart. So if you can see, I mean, if you see it here, the folding and the identification will not, it will look like as though the surfaces have self-intersection, but this is happening in the hyperbolic world, right? So you can just do an Euler characteristic computation and see exactly what kind of surface when you're identifying these pieces, what are you going to get? That's pretty simple. So these are the possibilities. You're going to cylinder, pairs of pans. Here also you get a cylinder, then pairs of pans forms cylinder and a 4-hole sphere, right? These are so what we are doing is we are breaking it apart and piecing them back together in and seeing what are the possibilities that come together. Pairwise, we are pairing them up. Break them and then pair them up. Okay? Some pieces we leave them aside as on their own. Some we pair up. And the pairings will lead to these possibilities. These kinds of subsurfaces, in fact, in your manifold. And so what we were able to show that if you take these curves, as you can see here, it's not always possible that these arcs that you get are curves on your surface, right? It might happen that when you cut across these geodesics are not closed geodesics. They might just be arcs. So the problem, so we had to take care of that. So we said that you take the there exists a sub-collection of curves in these geodesics, which are closed geodesics, which will yield a Pan's decomposition of your surface. I mean, not all geodesics are closed in the collection of geodesics I have described, but there'll be a bunch of closed geodesics. You can take such a sub-collection of geodesics in that collection we have described. That will always give you a Pan's decomposition. And not only that, this Pan's decomposition will be bounded about by the burst constant. Okay? And the proof is very simple hyperbolic trigonometry, if I may. So the first part is that if it has a subcollection that gives a Pan's decomposition, it's simple Euler characteristic argument. So I'm not getting into that. This part, what you can see is, if you take the center of the polygon, and if you take L1 and L2 be the lengths of the geodesics joining 0 to the initial point of A2I minus 1 in this polygon. A2I minus 1 on this polygon, the center to A2I minus 1. Okay? And similarly, if you have the geodesic joining center to A2I, it can be shown that the lengths of the curve C are bounded about by 2 times maximum of A and B, where A and B are these simple hyperbolic things. It's just I know the polygon completely, I can compute this explicitly. Right? And you can show that these quantities are bounded above by the lower bound of Buser for the burst constant. Yeah. That's simple. You can just do some basic, and you can show that it's bounded above by the lower bound by Buser for the burst constant. Okay? So that solves part of the problem, at least most of the problem. We can get, for these structures, we can get a Pan's decomposition which is bounded above by the burst constant. And then, so the second part of the problem is, how do you estimate it in the Pan's graph? Right? How do you estimate the distance between Pan's and Pan's graph? But that we can do it purely combinatorially. So what you can do is, for each polygon, you have a decomposition. You just have to keep track of what you are decomposing and what you are putting back together and in what order. Right? This is purely combinatorial. Right? And that's exactly what we need to compare the processes of decomposing the PFI and then piecing them back together. Okay? And to streamline this comparison, we need a combinatorial encoding of this process. So this process of taking it apart and putting it back together is simple is sort of a combinatorial process. You can make it a purely combinatorial process, right? And in order to do that, we define a simple map from a set of 2G points to a set of G points and a canonical 2G tuple, which puts some conditions on it, basic permutation conditions, right? That essentially captures this process, right, completely. That it's not only the decomposition, but how you are piecing it back together in a certain way, keeping track of what is getting paired up with what is left alone, and stuff like that. Okay, and this is like a simple, you can encode this like a simple as a simple surjective map, which has all these conditions, right? So is that okay? Yeah. No, this is like a permutation. This is a transposition. Transposition in the symmetric group. I should have put an extra space between them. Yeah, they are product of transpositions. All of these are transpositions in the symmetric group. Okay? And as I said, it's an element in sigma 2G, the symmetric group on 2G letters. Yeah. I was careful that I used S suffix 2G for the surface and sigma 2G for the symmetric group. I didn't want to mix the two up, right? So that's it. Now, why does this in fact capture the decomposition process? You can actually see that you can break it down. If any admissible Pan's decomposition of PF can be represented by a canonical 2G tuple. So this process that we are describing can be described by such a tuple, like this function that I just described. Like you can see, though I have not written it in a very nice way, this is exactly the sort of function. These are the rectangles that you got over here. Remember them? Recalling R1, R2, R3, R4. And these are the pieces that we have got to keep track of, right? So these are the pieces that we have got to keep track of and how you put them together. And so, yeah, so we can actually write a sequence like something like this, and this can be rearranged like this, sort of, right? And so for each case that we hit, like the first case I'm taking n1, n2 not equal to 2, n1 is even, n1 is odd, always you can take this decomposition, the fact that you're putting it together as a canonical. And here you can see that the adjacent ones are getting paired. If you are wondering what this inverse notation means, I had written it here somewhere. Yeah, here it is. So let Ri be the quadrilateral bounded by these, and Ra is represented by a pair of this. Ra inverse is just a complementary pair that you associate to it. Okay? So for each possible scenario, you can find a canonical tuple that sort of combinatorially encodes this decomposition and this process of piecing it back together. Okay? Now what you can do is, you can define a distance between these tuples in a very algebraic, simple, like algebraic kind of way. So what you can say, the distance between F and df and F2 is the minimal length of a word, sigma I, that represents this in sigma 2G, written as a product of transpositions. Okay, but word means that I'm taking a word in sigma 2G, which is a symmetric group, and I'm writing each symmetry as a product of transpositions. And what is the minimum between two such things? And that is basically I'm defining to be the distance. And the distance between equivalence classes, so I defined an equivalence class here. See, if two tuples are equivalent, if one of these things hold, and that I defined as an equivalence class, because I want to remove redundancies, right, while I'm doing this process. So the distance between equivalence classes will be denoted by D, and this is just the minimum of the distance, taking all representatives of the class, right? Now, this completely encodes the Pan's graph distance. As you can see, that replacing a curve by another that intersects it minimally changes the distance between the corresponding tuples by 1. Like what we did here, if you replace this by something it's completely sort of, the way I said it earlier, right. Yeah, so the way this distance is sort of set up, it's by fundamental design captures the distance in the Pan's graph, because it keeps track of everything. Say the minimal intersection and how it is put together, but everything is encoded in the way you put the pieces back together. And this gives an encoding for the distance in the Pan's graph. So you could do it directly if you want. I mean, you can take the thing and take some trouble and go into the Pan's graph and do it, but this gives you a purely combinatorial approach to this, which is what we wanted to achieve. Rather than doing it like getting your hands dirty, taking the actual Pan's complexes and trying to figure out what the distance would be, this gives you a combinatorial way of approaching it. It's pretty simple. Just take the corresponding canonical tuples and compute the distance in the way we are saying it. That gives you the distance in the Pan's graph. And thus, putting it all together, we have the result, right? So if you have F1 and F2 be reducible type 1 actions, and these are the corresponding structures that you realize them as isometries, then the Weil-Petersson distance, right? And here, this means that I forgot to put the star above it. I meant the orbits in the Teichmüller space. These are the orbits of the mapping class group orbits of these structures in Teichmüller space. Or if you may, you can think of mu Weil-Peterson as PF1 and PF2 in the moduli space. And that is bounded above by k times this distance between the corresponding tuples associated with the decomposition of the polygons associated with these actions, plus epsilon. And k and epsilon are the quasi-isometric constants coming from Brock's work. It's, well, thank you.
Any questions for Kashyap?
Yep.
Why is there a discrete set of points fixed by the map, or sorry, maybe why is there a single point in the Teichmüller space fixed by
The
mapping
irreducible action?
class? Yes.
Because they are, see, the quotient orbifold is this, right? Something like this. So any fixed point would correspond to a structure that you can put on this. What are the structures that will realize the action as an isometry? It's a structure that you can put on the quotient orbifold and pull back. How many structures can you put on this? An object like this. Right? In fact, this is generally a characterization for irreducible actions. Like if the quotient orbifold descends down to something like this, then it's pretty much like an irreducible action in general. It doesn't have to be just cyclic. Even for subgroups, you can think about it. Right.
Just there's no local information. To show that it's unique, you need some more argument.
Some more argument. Yeah, so we can also take the polygon directly and show that that polygon will be unique. That's in the papers also we can actually show that. Directly you can show that the polygon with the isometry will be uniquely determined. You can also show it directly.
Any other question?
Okay. Some time ago you mentioned that that any finite subgroup of the mapping class group can be realized
As a group of isometries.
As a group of isometries. Is it true for all surfaces or just the finite area ones?
This is for genus G. So if you take mapping class groups of surfaces with boundary, they will not have torsion.
Yes,
They will not have torsion. So this particular thing that I'm talking about will be relevant to maybe genus G surfaces and closed orientable. That is, we are talking about finite, finite type. We are talking about finite type here. Either genus G or genus G with n mark points. For them, it will be relevant. Right, what you're saying, because they will have finite order maps. They will have torsion. The other, like if you have boundary of a surface with a non-trivial boundary, that will not have torsion.
Yes.
So this becomes irrelevant. If you're talking about finite subgroups, right? So it becomes irrelevant. So you need genus G where there is torsion, or genus G with n mark points or punctures, if you may. Right? We see it as mark points in the mapping class group setting. Genus G with SGN, we call it. There it is too.
All right. If there are no further questions, let's thank